Let's look at vector calculus. Basically, we apply the calculus way of thinking to vectors. So we look at infinitesimals. So for example, if we have a curve and the position P as a vector at a time t, and we wish to find the velocity at a moment. So it's going to be something like that. What we can do is we can take points P at a little bit later than t plus epsilon, or let's call it delta t. And we can look at the slope we get from this. Sorry, the vector we get from this. And then we say that P at t differentiated is the limit as delta t shrinks to 0 of this vector, so from there to there, which is pt plus delta t minus pt over, maybe as these are vectors, I should be careful to write 1 over delta t. I was going to just write over like that, but I think that looks a bit nicer. So notice it's the same thing that we did in basic calculus, where we had y equals some function of x, and we wanted to know the slope at this point, so we just took points nearby and we said if x changes by a little amount here, call it delta x, then y changes by a little amount, change in y, which is just f of x plus delta x minus f of x, and the slope is the limit as delta x tends to 0, delta y by delta x. I've used different deltas, haven't I, so I could be consistent. Switch these back. Doesn't really make any difference which ones you use here. So this is the limit. Delta y was just that. Yeah, same deal. So we could use this to differentiate sine and cos. So suppose our position here for a given theta, our position for that theta is equal to the vector cos theta sine theta. And we wish to know what is the velocity. So the velocity is going to go perpendicular to the position. Haven't drawn that quite right because this should be a right angle, but if I mark it in, that will indicate. So this is our velocity for a given theta, which is the derivative of the position for that theta. So we just take a point a little bit further along our curve, call that change in theta, and notice that this arc length is just the same as that angle, change in theta. Yeah, this is a unit circle. So the arc length of a sector of the unit circle is equal to the angle in radians. So can you see that as delta theta tends to 0, the velocity at theta is going to approach this vector, but with a length of delta theta. So what is this vector? Well, it's perpendicular to this vector. So here we went along cos theta, and then we went up sine theta. So to get perpendicular vector, we go up cos theta and back sine theta. That's what we should be aiming for. And so we're going up by cos theta and back by sine theta. So this vector there, P dash, is minus sine theta cos theta. And these vectors are parallel. So a unit vector in this direction would be minus sine theta cos theta, and the length of that vector is ultimately this arc length. So as theta changes by delta theta, our P changes by delta theta minus sine theta cos theta. And this is delta p, the change in p. So for a given change in theta, what's our change in p? It's this. So we could rewrite this, maybe if I put this up here. So divide both sides by delta theta, and we get change in p by change in theta is equal to minus sine theta cos theta. So our cos theta sine theta vector differentiates to minus sine theta cos theta. So that simultaneously gives us cos differentiates to minus sine, and sine differentiates to cos. So sine differentiates to cos, cos differentiates to minus sine. What's minus sine going to differentiate to? So here's sine theta, and here's minus sine theta, and for a given point you can see the slopes are just going to be the opposite. Yeah, for a given x we're going down by this amount. Now for that same given x we're going up by the same amount. So minus sine is just going to differentiate to minus cos, which will differentiate back to sine. Now you might question, we haven't been rigorous in saying that this derivative is perpendicular, is a tangent to the circle. But we can formalize that very easily. Let's look at it. Let's blow up a picture. What we can do is, instead of using the limit of from here to here, from theta to theta plus delta theta, we could go back a certain amount and then go forwards by the same amount. So that angle there is theta, and both of these angles are delta theta. And so we could, there's P for our theta. That's P theta minus delta theta, and P for theta plus delta theta. So instead of looking at this chord as we shrink delta theta to 0, let's instead look at this chord. So we could rephrase this as the same thing as the limit, as delta t tends to 0 of, but now we've covered the distance over theta of 2 delta theta, so it's 1 over 2 delta t p of t plus delta t minus p of t minus delta t. Yeah, same deal. This formulation I prefer because it is symmetrical, and sometimes that symmetry simplifies the calculation. So, for example, if we've got, go back to our famous y equals x squared example that everyone uses to demonstrate calculus. So here's our point x, and here's our point x plus delta x, let's call that h, and here's a point x minus h. So if I look at the slope of this triangle, I've now got going across 2h, and what's this? Well, it's x plus h squared minus x minus h squared, which is equal to, it's going to be x squared minus x squared, 2hx minus 2hx, but we're doing a minus minus 2hx, we get 4hx, and h squared minus h times minus h, that's another h squared, so that's going to cancel. So this simplifies to 4xh, so that's change in y, that's change in x, so change in y by change in x equals 4hx over 2h equals 2x. So the reason people don't use this symmetrical formulation to motivate calculus with this example of y equals x squared is because x squared has this property that if you take a point x, then you advance your distance h forward and backward, and this chord you get is always going to be parallel to the tangent line. So that's kind of an interesting factoid about a parabola. Take our x and let's make our h really big. So this chord from these 2 points we've just shown it has the same slope as the tangent at this point x, parallel lines. And so returning back to this picture, you can see that this line is always, by symmetry, perpendicular to the radial line going from the origin to P. So in the limit, it's also going to be perpendicular. So let's have a go at doing this formally. We've got our P derivative of P for theta is equal to the limit as delta theta tends to 0. I'm just going to write delta, but I mean delta theta, of P theta plus delta minus P theta minus delta over 2 delta. And what is P of theta plus delta? That's just cos of theta plus delta sine theta plus delta. And using double angled formulae, you'd expand those out to get cos of theta cos of delta minus sine theta sine delta sine theta cos delta plus cos theta sine delta. And similarly for p theta minus delta, well, it's just going to be the same thing, except we're replacing delta with minus delta. So cos theta cos of minus delta is cos theta cos delta, because minus delta is, cos of minus delta is the same as cos of delta, because cos is an even function. So minus sine theta sine of minus delta, but sine of minus delta is minus sine of delta, so that goes to a plus. Cos theta cos delta, sorry, cos of minus delta, which is cos of delta, and then plus cos theta sine of minus delta, so that's minus cos theta sine delta. So if you subtract those, these are going to disappear, and you've got that minus that, which is just minus 2 sine theta sine delta. And the y component, that minus that. The first term again is going to go, and you're just left with that minus minus that. So we've got 2 cos theta sine delta. Which is equal to 2 sine delta minus sine theta cos theta. Okay, so that was our change in P. And our change in theta was 2 delta theta. So I have to be careful of notation here. Change in P and change in theta was 2 delta theta. So the change in P for a given change in theta is equal to 2 sine theta minus sine theta cos theta over 2 delta theta. And obviously the 2's will go. And so now we just have to prove that sine theta over delta theta tends to 1 as theta tends to 0. Delta theta tends to 0. So let's have a go at that. I've made a mistake here. This was sine of delta theta. So here's our delta theta. And this is cos delta, and this is sine delta. and we are required to prove that sine delta over delta tends to 1 as delta tends to 0. Now, can you see this arc length is just delta? So what we're required to prove is that this line, in the limit, the length becomes equal to this arc, and it's intuitively obvious. You can imagine just shrinking this angle. The line is going to get a better and better approximation for this segment as the segment is becoming more and more vertical. But to do it rigorously is a little bit trickier. So one clever way of doing it is to look at the outer triangle. And what's this length here? Well, it has the same slope as this sine theta cos theta triangle, so call that question mark, and so question mark over 1 is equal to sine theta over cos theta. We're using delta. Sine delta over cos delta. And now we can make an inequality on the area of the smaller triangle, the area of the sector of the circle, and the area of the big triangle. And we can say the area of the small one, which is a half cos delta sine delta, is less than the area of the sector, which is just, well, the area of the whole circle is pi r squared, which is pi, and we're looking at delta over 2 pi times pi, otherwise known as delta over 2, half delta, which is less than the area of the big triangle, which is 1 times sine delta over cos delta. And we've got sine delta on either side, but we want to sandwich sine delta in the middle, so we just divide through by sine delta. So, we wanted a half there. So first let's get rid of all the halves. And now let's divide through by sine delta, so we get cos delta is less than delta over sine delta is less than 1 over cos delta. So delta over sine delta is between cos delta and 1 over cos delta, so just flip everything and you get sine delta over delta between those 2 points, because 1 over cos delta flipped is cos delta, and likewise but as delta shrinks to 0, cos delta clearly it becomes 1 in the limit. So both these things tend to 1 as delta tends to 0. Therefore, this thing also tends to 1 as delta tends to 0. Okay, done. Note that you didn't need to consider sine and cosine. Both together you could have just started by drawing your sine wave, and you could have picked an x and you could have looked at x minus h and x plus h. And you could have looked at sine of x plus h minus sine of x minus h over 2h, taking the limit as h tends to 0. Now, without a doubt, this is the way that you will see the derivative of sine x or cos x presented in a textbook or probably on Wikipedia. But if you go at it from this direction, it's very easy to miss the elegant intuition of working from the unit circle, i.e. you end up getting mired in technical details and heavy working, and this trick isn't particularly pleasant for sine x over x because it's difficult to come up with. It's clever, and a mathematical proof shouldn't be clever, it should be elegant. Elegant trumps clever. In this particular example, I've gone through the formal mechanism to illustrate how you would go about differentiating an arbitrary vector function. But in this particular case, you can shortcut. There's a more elegant way of seeing it, just in the same way that for differentiating y equals x squared there is a more elegant way. You can use symmetry of x minus h and x plus h, and you don't have to fiddle with infinitesimals. This approach I've never seen anywhere before, so it's something I came up with. As far as I can see, it can be formalized completely, so no further working is necessary. One mistake that I have made in this whole video, and I put a text bubble up earlier, is that I have been misusing my deltas. I should here be writing p of t plus delta t, not big delta t. Yeah, little delta t is a small amount of t, and big delta t would be change in t. So I will have to redo this video at some point and sort out my terminology because it's shoddy. So I fell over here where I was looking at change in p by change in theta, but I'd already used these delta symbols elsewhere. So this thing I want to be 2 delta theta, so I need to switch this out with deltas everywhere, little deltas. So my to-do list for a final version of this video would be get my deltas right, why am I suddenly going from t to theta here and then talking about velocity? That's dumb. I should be using time as my dependent variable, because you differentiate a function of time and you get the velocity. So this would be t not theta.